This question is about acids and alkalis. Acids and alkalis are substances that produce ions in aqueous solution. Draw one line from each substance to the ion always produced by that substance in aqueous solution. You can see we've got two substances, acid and alkali, on the left-hand side, and we've got 5 options for the ion which is always produced in aqueous solution on the right-hand side. And we've got 2 marks for this question, which will be 1 mark for each line. Acids are characterised as being substances which will ionize, which means they will dissociate and fall apart in aqueous solution and produce hydrogen ions. You can see from these 2 examples where we've got hydrochloric acid, which has got the formula HCl, and sulfuric acid, which is the formula H2SO4. Both of these are strong acids and they will dissociate into hydrogen ions and a second type of ion. And so we need to connect the acid substance to the hydrogen ion on the right-hand side. And you can see that Cl- and SO4 are clever decoys for this question, because hydrochloric acid will produce Cl- in addition to the H+, and sulfuric acid produces the SO4 in addition to the H+. Alkalis are characterised as substances which will ionize and produce hydroxide ions in aqueous solution. That means OH-. And a good example of that is sodium hydroxide, which has got the formula NaOH, and when that dissociates into its ions, you get Na+, and you get OH-. And so we need to connect the alkali to the OH-, and again we've got quite a plausible decoy here for Na+ as another option, and that's because sodium hydroxide will produce Na+ ions, but a different alkali, for instance potassium hydroxide, would produce K+, and it would produce OH-. And so alkalis will produce OH- in aqueous solution. 1 mark for each of those lines. What type of aqueous solution has a pH of 11? You need to remember the pH scale goes from 0 to 14, where 7 in the middle is neutral. And lower than 7 is an acid, and the further away from 7 you get, the stronger the acid is. Anything with a pH above 7 will be an alkali, and the further away from 7 you get, the closer to 14, the stronger the alkali will be. This means that if we have an aqueous solution with a pH of 11, this is greater than 7, so this will be an alkaline solution, and we'll get 1 mark for ticking the central box. A student determined the reacting volumes of hydrochloric acid and sodium hydroxide solution by titration. This is the method they used. Measure 25 cubic centimetres of the sodium hydroxide solution and then add the sodium hydroxide solution to a conical flask. Add 3 drops of indicator to the sodium hydroxide solution. Add the hydrochloric acid drop by drop until the indicator changes colour. Record the volume of hydrochloric acid added. Repeat steps 1 to 5 3 more times. Which piece of equipment should be used to measure 25 cm cubed of the sodium hydroxide solution in step 1? We've got 3 options. Option 1 is a beaker. A beaker is nowhere near accurate enough. It's very difficult to accurately measure any kind of volumes in a beaker. That's for carrying out a chemical reaction in rather than anything else. Pipette is our next option, and this is the correct answer. There are a variety of different types of pipettes. We've got dropping pipettes, which you wouldn't typically think would be the best way of adding your sodium hydroxide solution, but we can also have pipettes that are designed to very accurately measure a specific volume. And so 25 centimetres cubed of sodium hydroxide solution could be measured very accurately with one of these pipettes of this type. And a ruler, that's no good. Rulers are good for measuring lengths, not for volumes of liquids. In part D, we're asked which piece of equipment should be used to add the hydrochloric acid drop by drop in step 4. Well, you can tell from my picture what the answer is here. I didn't write the name next to it, but this is a drawing of a burette. Burettes are specially designed to measure accurately a volume of a liquid which we don't know in advance. So we keep adding a little bit, then a little bit more, drop by drop, as it says in the method. We swirl our mixture as we go. We're looking for a colour change of that indicator. And when the indicator changes colour, we stop our titration and we look at the burette and we record the volume that we've added from the burette by looking at how much extra space we've got in the burette that we didn't have at the start. Balance is a decoy answer. We use balancers to measure the masses of substances, and the measuring cylinder is the most plausible of the two wrong answers. We do use measuring cylinders to measure volumes, but they're not very good at measuring unknown volumes as accurately as burettes are. The table below shows the results for a titration. You can see we've got 4 trials. That means they've done the experiment 4 times, and we've got a different volume of hydrochloric acid added in cm cubed each time. So you can see we've got 24.3, 24.5, 28.1 and 24.4. And we're being asked which is the anomalous result in the table above. An anomalous result is a result which doesn't fit in with the others. So this experiment has been done 4 times, and we would expect the results to be close to each other each time because the same thing was carried out. But one of these values is significantly greater than the other 3. 24.3, 24.5 and 24.4, they are all very close together. 28.1 is much larger, so we need to tick the box for trial 3. Then we're asked to suggest one reason for the anomalous results in the table above. Well, there are a few reasons why titrations can go wrong. The first reason is that they maybe added too much hydrochloric acid from the burette. You should add drop by drop close to the end of the titration. But if you added it too quickly, then you might miss the point of the end of this titration. Or perhaps the hydrochloric acid was added correctly, but they didn't swirl the conical flask. And swirling the conical flask encourages the acid and the alkali to mix together, and that means that the acid that you've added will react with the alkali before you add the next portion of the acid from the burette. Alternatively, they might not have rinsed the apparatus after the previous trial, which would mean that there would have been some chemicals left over in the conical flask, which meant the results would have been affected in that way. Or they could have not used a white tile during the titration, and this would mean that they might miss the colour change because they had a confusing background underneath the conical flask, and so they couldn't catch the point at which the indicator changed colour. Or one final thing that we could say is that maybe they misread the burette when they were seeing how much they'd added during the titration, or they could have misread the pipette in the first place and maybe added too much alkali to the conical flask, which is why we needed to add more hydrochloric acid from the burette than we were expecting. Any of those things, absolutely fine. We only need to say one of them, that's in bold, 1 mark for any one of these suggestions. The student used a solution of sodium hydroxide of concentration 4.00 grams per decimetre cubed. Calculate the mass of sodium hydroxide in 25 cm cubed of this solution, and we're told that 1 dm cubed is 1000 cm cubed. There are 3 marks available for this question. One of them will be for our final answer, which is the mass in grams. And the first thing that we need to do is look at the quantities we've been given. 4 grams per decimetre cubed, that's our concentration, and 25 centimetres cubed is our volume. And so those units don't match up. They've both got some element of volume to them, but they are different units. And we've got the big clue here. We're being told 1 dm cubed is 1000 cm cubed. And so what we need to do is we need to work out how many dm cubed 25 cm cubed would be. And so quite clearly, 1 decimetre cubed is 1,000 times bigger than a centimetre cubed. And so what we need to do to turn 25 centimetres cubed into decimetres cubed is divide by 1,000. And when we do that, we get a volume of 0.025 decimeters cubed. So we now know what volume we've got of sodium hydroxide in decimeters cubed. And the concentration of 4 grams per decimeter cubed is equivalent to saying, if we had 1 decimeter cubed of this solution, we would have a mass of 4 grams of sodium hydroxide dissolved in it. Now, we've got quite a bit less than that, but all we need to do to work out the mass of sodium hydroxide is to multiply the concentration of 4 grams per decimeter cubed by the volume we've got of 0.025 decimeters cubed. And so when we plug that number into the calculator, we get a mass of sodium hydroxide of 0.1 grams. 1 mark would be for the volume conversion into decimeters cubed, 1 mark would be for the calculation, and 1 mark would be for our final answer.